Welcome back to Sleepy Physics Lab. Tonight we explore a question that has haunted scientists and dreamers alike for nearly a century. What if our universe is not alone? What if every choice you never made, every path you didn't take, exists somewhere in a world just like this one? What if reality itself is far larger, far stranger, and far more abundant than we ever imagined? This is the story of the multiverse. So settle in, let your breathing slow, and imagine with me. In 1957, a graduate student at Princeton University named Hugh Everett sat alone in his dorm room, staring at the equations of quantum mechanics. He was troubled by something that had bothered physicists since the 1920s: the strange, almost dreamlike behavior of the smallest particles in existence. An electron, it seemed, could be in two places at once, until someone looked at it. Then, it would choose. But what happened to the other possibility? Where did it go? For decades, physicists had accepted an uncomfortable answer. They called it the Copenhagen interpretation, and it said essentially that the other outcome simply ceased to exist, collapsed into nothing, because someone observed it. But Everett couldn't accept this. He thought it was absurd, that consciousness should have such power, that the universe should care whether anyone was watching. So he proposed something radical, something that would take decades to be taken seriously. What if the other outcome didn't disappear? What if both outcomes happened, just in different worlds? Imagine you are standing at a crossroads. To your left, a path through an old forest, dark and quiet. To your right, a road along the coast where you can hear waves in the distance. In our everyday experience, you choose one, and the other path fades away, becomes a story of what might have been. But in Everett's universe, you take both paths, not in this world, but in two worlds that now exist side by side, separate, unaware of each other, both equally real, both equally you. Every quantum event, every tiny interaction between particles creates this split, not once in a while, not rarely, but billions of times, in every instant, in every corner of the universe, an endless branching, a garden of forking paths, growing, expanding, forever. This is why physicists call it the many worlds interpretation, not a theory of distant places, but of here, of now, of you, somewhere in the vast tree of possibilities. There is a version of you who made every different choice, who said yes when you said no, who stayed when you left, who took the risk when you hesitated, who spoke the words you kept inside. These are not ghosts, not dreams, not fiction. If Everett is right, they are as real as you are, living their lives, wondering about the paths they didn't take. Just as you wonder now, in one world, you took that job in another city. In another, you stayed. In one, you said hello to a stranger. In another, you walked past. Each choice, a branching, each moment, a new universe, and all of them equally real, equally valid, equally alive. To understand why Everett was so troubled, we need to look closer at what troubled all quantum physicists: the measurement problem. Before observation, a quantum particle exists in what physicists call a superposition, a kind of ghostly mixture of all possible states. It is not here or there, it is here and there, not spinning up or down, but both at once. This is not poetic language. This is what the mathematics demands. This is what experiments confirm. The double-slit experiment, performed countless times, shows that a single electron passes through two openings simultaneously, creating an interference pattern, as if it were a wave, as if it were everywhere at once. But when we place a detector, the wave collapses. The electron chooses and the pattern disappears. For decades, physicists accepted that consciousness or measurement caused this collapse. But Everett asked, what if there is no collapse? What if the electron is still in both places, but we, the observers, have split too? What if, when we look, one version of us sees the electron here, and another version, equally real, sees it there? Both outcomes preserved, both worlds real, neither more true than the other. But there is another kind of multiverse, not born from quantum splits, but from the very birth of reality itself. In the first fractions of a second after the Big Bang, the universe expanded faster than light, not the matter within it, but space itself, stretching, pulling, growing at a rate that defies intuition, creating a cosmos so vast that light from one end has not yet reached the other, and may never. In this period, which physicists call cosmic inflation, quantum fluctuations, tiny ripples in the fabric of space, were frozen into place, becoming the seeds of galaxies, the architecture of the cosmos. But what if, in some regions, the inflation stopped sooner or later? What if, in the endless stretching, different patches settled into different states? What if the laws of physics themselves settled differently? Physicists call this the eternal inflation model. Our universe, a single bubble, in an infinite ocean of other bubbles, each with its own physics, its own constants, its own story. Some with gravity too strong, collapsed back into nothing moments after birth. Some with gravity too weak, never forming stars, cold and dark forever. Some with different dimensions, where space has 4 or 5 or 20 directions. And some, like ours, balanced perfectly, a cosmic accident, a fortunate universe, where atoms can form, where stars can burn, where life and consciousness and you can exist. This leads us to one of the deepest mysteries in cosmology, the fine-tuning problem, the constants of nature, the numbers that determine how physics works. Seem improbably perfect for life. If the strong nuclear force were slightly weaker, protons and neutrons wouldn't bind. No atoms, no chemistry, no us. If it were slightly stronger, stars would burn out in millions of years instead of billions. Not enough time for life to evolve. If gravity were stronger, stars would be smaller, burn hotter, die faster. If weaker, stars might never ignite. The cosmological constant, the energy of empty space, is 120 orders of magnitude smaller than quantum mechanics predicts. Yet if it were larger, the universe would have expanded too fast. No galaxies, no stars, no planets. Why? Why these numbers? One answer is the multiverse. If there are infinite bubble universes, each with randomly determined constants, then of course we find ourselves in one where life is possible. We couldn't exist in any other. This is the anthropic principle. Not an explanation, but a selection effect. Like asking why Earth is the perfect distance from the sun. There are billions of planets. We had to be on one that supports life, or we wouldn't be asking. There is yet another way to imagine the multiverse, and it comes from the strangest place of all, mathematics. In 2003, the cosmologist Max Tegmark proposed that every mathematically possible universe exists, not because someone created it, not because it evolved, but simply because it can be described. Think of it this way. If you write down every possible equation, every possible set of physical laws, each one describes a universe. And if mathematics exists independent of minds, independent of space and time, then all these universes exist too. Not in some distant place, not in another dimension, but as real as the numbers themselves. This is the level 4 multiverse, the ultimate multiverse, where every possible reality, every possible variation, every possible you is not just possible, but actual. In this view, our universe is not special. It is simply one structure. In the infinite library of mathematical structures, some simpler than ours, some more complex, all equally real, all equally valid. Let us pause for a moment and consider what this means. Not in the abstract, not as physics, but as life. Think back to a moment when you stood at a threshold, a door was open, and you walked through, but another door closed. Perhaps it was a job you didn't take, a city you didn't move to, a person you didn't speak to, a word you held inside. In our single-track minds, these are ghosts, haunting what-ifs, the road not taken, the life not lived. But in the multiverse, these are not ghosts. They are as real as this moment, as real as your breath, as real as the weight of your body against the surface beneath you. Somewhere, you took that job, you moved to that city, you spoke those words, you lived that life, and that version of you is not a stranger, is not an imaginary friend, is you just as much as you are you. This is the strangeness of Everett's vision. It does not diminish our choices, it multiplies them. It does not make our path meaningless, it makes every path meaningful. The you who took the risk and the you who played it safe, both are real, both are valid, both are living their consequences, learning their lessons, growing in their own ways, and perhaps, in some quiet moment, in some late night. That other you wonders about you too, wonders what would have happened if they had chosen differently, if they had become you. You might think that quantum mechanics, the realm of electrons and photons, has nothing to do with your morning coffee, your commute, your conversations. But consider every chemical reaction in your body, every neural firing in your brain, every beat of your heart depends on quantum mechanics. The electron transfers that power your cells. The molecular bonds that hold you together, all of it, governed by the same strange rules that allow particles to be in two places at once, that allow cats to be both alive and dead. Until observed, every moment of your existence is built upon this quantum foundation. And if ever it is right, every quantum event in your body, every electron that could go left or right, does both in different branches of reality. Your body itself is constantly splitting into countless versions, each slightly different, each equally real. The you who finishes this sentence and the you who stops halfway both exist, both continue, both have their own futures, their own stories, their own sleeps. Let us zoom out, far beyond our daily lives, beyond our planet, beyond our galaxy, to the largest scales of existence, the observable universe, 93 billion light-years across, containing hundreds of billions of galaxies, each with hundreds of billions of stars, a number so large it defies comprehension. And yet, if eternal inflation is correct, this vast cosmos is but a single bubble in an ocean of bubbles, each bubble as large as ours, or larger, each with its own physics, its own history, its own life. Perhaps in some distant bubble, the strong nuclear force is slightly stronger, stars burn hotter, live shorter, planets form differently. Life, if it exists there, is nothing like life here. Perhaps, in another bubble, gravity is weaker, galaxies spread thin, never quite coalescing, a cold, dark, empty place. Or perhaps, in some bubble, the conditions are just right. Not just for life, but for consciousness, for intelligence, for beings who can look up at their stars and wonder, just as we wonder, are we alone? The multiverse suggests we are not, but also that we can never meet our cosmic neighbors, separated by distances that make our universe seem like a single grain of sand on an endless beach. You might wonder, can we ever know? Can we ever see these other worlds? Travel to them? Speak across the divide? The honest answer is probably not. The many worlds once split drift apart forever. Decoherence, the entanglement of a quantum system with its environment, makes the branches irreversible. The other bubble universes, separated by distances that make our cosmos look like a grain of sand, expanding away from us faster than light could ever travel. The mathematical universes, existing in a realm beyond space and time entirely, unreachable by definition, and yet there is something beautiful in the not knowing, in the possibility that somewhere, in the endless garden of forking paths, another version of you is lying here, listening to this same story and wondering about you. Perhaps in some unimaginable future, some civilization will find evidence, a signature, in the cosmic microwave background, a collision between bubble universes, a statistical anomaly that only the multiverse explains. But for now, we have only the mathematics, the logic, the dream. There is a strange comfort in Everett's vision in the multiverse, every possibility realized, every choice preserved. Nothing is ever truly lost. The conversation you wish you'd had, the love you wish you'd expressed, the life you wish you'd lived, all exist, somewhere, not as regrets, but as realities. Other versions of you are living them, and perhaps, in some sense, that is enough. The multiverse does not ask us to do more, to be more. It simply says, everything you could have been, you are, somewhere, in the infinite branches, in the eternal tree, in the garden of forking paths. The multiverse, whether it is real or merely a dream of mathematics, asks us